Everything you see is a story of chemistry. The chair you are sitting on, the air filling your lungs, and even the thoughts running through your mind are all governed by the silent, invisible rules of chemical interaction. We often think of chemistry as something confined to a laboratory with bubbling beakers and strange smells, but it is far more than that. It is the fundamental science of what things are made of and how they change. Understanding chemistry is like being given a secret decoder ring for the universe itself. It reveals the hidden architecture behind the everyday world, from the rusting of an old car to the creation of a star. This essay will guide you through the essential concepts of this fascinating field. We will start with the smallest possible unit of matter, the atom. From there, we will explore how these atoms combine to form the elements and molecules that construct our reality. We will look at the different forms matter can take: solids, liquids, gases, and understand what holds them together. The journey will then take us through the periodic table, chemical bonds, and chemical reactions. An atom is the smallest unit of an element that still retains the properties of that element. Imagine taking a piece of pure gold and cutting it in half, and continuing this process over and over. The smallest possible piece you could end up with that is still identifiable as gold would be a single gold atom. These particles are so incredibly small that you cannot see them with your naked eye or even with most standard microscopes. A single drop of water, for instance, contains billions of trillions of atoms. They are the fundamental bricks from which everything in the universe is constructed, distant stars, the very cells in your body. At the heart of every atom lies a dense core called the nucleus. This central region is where most of the atom's mass is concentrated. The nucleus itself is composed of two types of particles: protons, neutrons. Protons carry a positive electrical charge. Neutrons, as their name suggests, are neutral. They have no electrical charge at all. The number of protons in an atom's nucleus is what defines it. This defining number is called the atomic number. Swirling around the central nucleus in a cloud of motion are the electrons, much lighter and negatively charged. In a neutral atom, the number of negatively charged electrons is exactly equal to the number of positively charged protons, balancing the atom's overall charge to zero. The attraction between the positive protons and negative electrons holds the atom together, preventing electrons from flying away. The electrons exist in specific energy levels, or shells, and it is the electrons in the outermost shell that are involved in forming connections with other atoms. These interactions, which we will explore later as chemical bonds, are the basis for all chemical reactions and the formation of the molecules and compounds that make up our world. The simple structure of the atom is the starting point for all of chemistry's complexity. An element is a pure substance consisting of only one type of atom, distinguished by its specific number of protons. Think of elements as the fundamental alphabet of chemistry. The 118 known elements can be combined to form all the matter we see. Some elements are very common and familiar, such as oxygen. Others are much rarer and less known, like rhodium, promethium. Each element has unique properties. For example, gold is a shiny, unreactive metal. Chlorine is a pale green, highly reactive gas. When two or more atoms join together, they form a molecule, the smallest unit that can exist on its own and still retain chemical properties. Two oxygen atoms bond to form an oxygen molecule, O2. This pairing creates a stable unit essential for life. Water is one oxygen bonded to two hydrogens, H2O. Together, they form liquid water with properties different from its gaseous elements. When a molecule is made from two or more different elements chemically bonded together in a fixed ratio, it is called a compound. Water, H2O, is a compound because it is always made of two hydrogen atoms for every one oxygen atom. If that ratio were different, it would be a different substance entirely, such as hydrogen peroxide, H2O2. Another common compound is table salt, sodium chloride, NaCl, one sodium atom, and one chlorine atom. The properties of a compound are unique and often dramatically different from the properties of the elements that make it up. Matter can exist in several different physical forms, known as states of matter. In a solid, the particles are packed tightly in a fixed arrangement, vibrating in place, giving solids a definite shape and volume. In a liquid, particles have more energy, remain close, but move past one another, taking the shape of their container. In a gas, particles move rapidly and are far apart, so a gas has neither definite shape nor volume and expands to fill any container. Water vapor is steam. Melting, freezing, boiling, and condensation are physical changes. The H2O molecules remain the same. These ideas are part of our daily lives, food and cleaning products. Think of this as a map for a new and exciting territory. Each section is a landmark to navigate chemistry with confidence. We will see how salt is formed, how water exists as ice, liquid, and steam, and what really happens when something burns. The periodic table of elements is, one of the most powerful and iconic tools in all of science. It is a systematic chart that organizes all the known chemical elements based on their atomic structure and chemical properties. Each element gets its own box showing its name, symbol, like O or Phi, and its atomic number. The atomic number, the number of protons, is the key organizing principle. The table starts with hydrogen, atomic number 1, and proceeds in increasing atomic number across each row. Its genius lies in rows and columns, periods and groups. Across a period, each element has one more proton and electron than the one before. Elements in the same group share similar properties because they have the same number of valence electrons. Group 1 elements are highly reactive metals. Group 18, the noble gases, have full outer shells, very stable and unreactive. In contrast, halogens are one electron short of a full shell and are extremely reactive. With major contributions by Dmitry Mendeleev, the table is more than a list. It maps relationships among elements. It reveals patterns in size, reactivity, and other properties. Learning to read it is like learning a map of a new country. It helps you navigate chemistry. Chemical bonds are the persistent attractions that hold atoms together to form molecules and compounds. These forces are electrical in nature, arising from interactions between positively charged nuclei and negatively charged electrons. Without bonds, the universe would be a diffuse soup of atoms. Bonds create all complex substances, from simple water to intricate proteins. Atoms form bonds to reach more stable states, usually by filling their outer electron shell. There are two primary strong bonds, ionic bonds. Electrons are transferred. The loser becomes a positive ion, a cation. The gainer a negative ion, an anion. Opposite charges attract. Example, Na donates to Cl, forming Na plus and Kl that stick together. Covalent bonds. Atoms share pairs of electrons, helping each complete outer shells, a strong directional link. In water, oxygen shares with two hydrogens, forming two covalent bonds and a V-shaped molecule. Covalent bonds form most molecules in living things, especially carbon-based compounds. Ionic compounds form rigid crystals, dissolve in water, and conduct when ions separate. Covalent substances often don't dissolve or conduct. Bond type and strength determine melting point, hardness, solubility, and overall reactivity, the invisible glue shaping the material world. A chemical reaction is a process that transforms one set of chemical substances into another. Reactions involve breaking bonds in reactants and forming new bonds to make products, creating substances with new identities. Iron, oxygen, and water over time react to form rust, a flaky product unlike the original metal. Equations symbolically show reactions. Reactants on the left, products on the right, separated by an arrow. One molecule of methane reacts with two molecules of oxygen to produce one carbon dioxide and two water molecules. Equations must be balanced to conserve mass. Activation energy is needed to break bonds. Friction from striking a match provides activation energy. Some reactions release energy. exothermic, like burning wood. Others absorb energy, endothermic, like an instant cold pack. Rate increases with temperature, concentration, and catalysts that speed reactions without being consumed. Enzymes are biological catalysts that speed processes like digesting food and building new cells. In every reaction, atoms are rearranged. Old bonds break, new bonds form, and energy changes accompany the transformation. Acids and bases are two categories with distinct and opposite properties. Acids produce H+ in water, sour, like lemon juice and vinegar. Bases produce OH- or accept H+, bitter and slippery, like soap or baking soda solution. Acid and base neutralize to make water and a salt. pH runs 0 to 14. 7 is neutral. Lower is more acidic, higher more basic. Each unit is a tenfold change. A solution is a homogeneous, uniform blend. Solute dissolves into a solvent. Water is the most common solvent. Sugar dissolves in hot tea as molecules spread out evenly. Air is a gaseous solution. Steel is a solid solution of carbon and iron. Blood plasma is a complex aqueous solution, carrying nutrients, oxygen, and wastes. Dissolving and acidity matter for cooking, cleaning, medicine, and environmental science. Chemistry studies matter. All matter is made of atoms, which define elements. Atoms bond to form molecules and compounds. The periodic table organizes elements. Bonds hold matter together. Reactions transform substances under the laws of energy and mass. These principles shape daily life in every object you touch and every breath you take. And you can see them in action at home. Make a red cabbage indicator. Boil leaves for purple extract. It turns pink with acids and green with bases, bringing pH to life right before your eyes.